Well, hello, Machine Shop Math fans. We're back for part 2 of video 9, which is the explanation, instruction, and review that deals with Exam 2. Hopefully this week I'll have Exam 3's video redone and up. By now you should have gone through every video that I have posted in D2L week 1 and week 2. I'll have the email list to y'all shortly, or I should have that shortly. You'll be getting this in week 3, so we're only in week 1 when I'm making this video. All right, well, we're going to now talk about solid space and negative space, but before we do that, we need to clear something up. So we're going to go have a commercial word from our sponsor. This is brought to you by Dr. Demento, yours truly, in league with the Dr. Strangelove Institute for Real and Positive Thinking. I like to consider it real and right thinking, but that's neither here nor there. The mysterious case of the donut hole. Now, anyone with an IQ above 5 knows that that's not a donut hole. That is a ball. That's a sphere. It's a solid mass. It has mass to it, even though there's air in it from the dough being fried in hydrogenated grease. It's still a mass. It's a sphere. It is not a hole. But no, we call these donut holes. They're not donut holes. They're donut balls. So, you want the hole? You gotta buy the freaking donut. This is the hole right there. You see, there's no donut there. It's a hole. That's negative space. This is positive space, negative space. Yes, you want the hole, you gotta buy the donut. And if you just eat the hole, then you need to go to the local psych ward because you're just eating air. So if you truly bought a bag of holes, I got a bridge in Arizona I want to sell you. You'll just be eating air. These are not donut holes, they're donut balls. I hate to dispel that. You were told there was an Easter bunny once in Santa Claus. That was false. You probably had some lover tell you that it was forever, and then that didn't work out either. So just get over it. That's a donut ball. That's a solid mass. That is a mass. The hole is in the donut. What defines the hole is the mass around that hole. If there was no mass around it, it would just be air. So a hole is defined by the solid mass around it. Okay? And so we got that straight. So, negative space is the hole. A hole is negative space defined by the surrounding mass. The positive space surrounding it. The real hole is that empty round space in the center of the donut. That's right, it's the center round space with no donut material in it. If all you ate was the hole, the real hole, you would gain no weight and you're eating air. And like I said, you probably are in need of some psychological help. All right, so we hope we get this out of the way. Now, we want to thank our friends at the Dr. Strangelove Institute for Real and Right Thinking, or Real and Positive Thinking, and Dr. Demento. All right, so let's get back to our subject matter. So we got that. So the next time you go to the donut shop, I argue with the Vietnamese donut lady all the time at my donut shop, and she says I'm crazy. But those are donut balls. They're not donut holes. All right. No. So, solid space. Solid space and negative space. Positive space and negative space can also be referred to that. A hole in a solid reduces the volume. Yes? If we have a solid, let's say we have a solid. Oh my God, that is just really ugly. Jeez. Oh, I hate that. Oh my God, that's ugly. Here, let's just get rid of that. Delete. Come back over, activate the pin, go do mass. Okay. Let's say we have a solid. Okay. This is our solid. Now, how many sides do we have? We have one side here. We have this other side back over here, right? Hidden. Okay. So we have 1, 2, 3, 4, 5, 6 sides, do we not? 2 on the ends and 4. So 2 and 4 is 6. We have 6 sides. So that's our surface area. Whatever the area is of each one of these sides added together is our total surface area. Now our volume is bounded by this area here, yes, 2 dimensions area, times the third dimension, yes? Okay, so let's get used to doing our XY coordinates. Oh, excuse me. We'll call that Z, or the third dimension. We'll call this X, and we'll call this Y, believe it or not. Just crooked as I am at my age. All right, so we have X and Y, okay? This is X, this is Y, and this is Z. So our surface area is bounded by the area of all the sides. Our volume is bounded by that dimension there, X times Y times Z, and that's our volume. Now what if we bore a hole in this thing? We're going to bore a hole, or drill a hole. Okay. So if we look at it in section, oh geez. Probably should go back to the notes. I got better drawings over there. So if we look at this in section, we've got a hole drilled through it, or bored through it. Now we've reduced the volume, but we've increased the surface area, have we not? We've opened up more surface, but we've reduced the volume. Just get your head around this. This is the negative space, because we took solid mass away, and this remains the positive space. But we've increased the surface area, because now not only do we have the surface area of all 6 of the outsides, okay, now we have reduced the surface area on the end some, yes. So you'd have to run the calculation out, and we will do that at some point in the future to see how much you've increased your surface area. Now we know the ends, the surface area has decreased because it's no longer a solid plane. We've got a hole in there. But we also have the surface area inside this right in here, right? It's the inside of the toilet paper roll, or the hole. So if you were going to paint this thing, you would have to calculate how much surface area is inside here. And that's nothing but the circumference of the hole times how long the hole is. And that's your total area of the inside. Okay? We'll get back to that later. All right. Nope, that's YouTube. Let's go over here. All right. So that's a solid space. Now, I think we're okay to draw here in red. There we are. Okay, we're good. All right. We just found a hole is a negative space. We just found that the volume of the solid right circular cylinder. We did that before, right? Now let us bore or drill a hole down the longitudinal center line. Now we have a pipe, a hollow cylinder, etc., right? So let's say that the radius for the total cylinder before we bored the hole was 0.75, and that's still the radius from the center of the cylinder to the outside edge of the circumference. And then we bored a 1-inch hole on the inside, which means that it's a 1/2 inch radius, 0.5, right? So it looks like this in section. And we want to find the volume of this thing. Now remember, this is positive, and the hole is negative space. Don't be a donut ball goober. All right. Now, or don't be a donut hole goober. All right. Now you know the secret of the donut ball versus a donut hole. All right. So the volume is the area of the base. Now the area of the base is a circle, right? Times the height, or the length in this case. You're going to lay it down. All right. Height, length. This is the third dimension. Now there's two ways to do this. The first is to find the volume of the outer cylinder as if you didn't bore the hole in it, okay? All right. Plus the center cylinder, which is negative space. The resultant total is our real volume. Now, you can do this by finding the volume as if there is no hole in it, and that gives you a large volume. In this case, it's pi r squared times the height. That's pi times 0.75 squared times the length, which is 1.75 inches. We said the height or length is 1.75 up here. This gives us a volume without the hole of 3.092505268 inches cubed. It's volume. It's got to be cubic inches, remember? Now we're going to calculate the volume of negative space of inside there. That 1-inch hole we bored through there or drilled through there. All right. So I'm going to put a negative. I put a negative in front of mine so I don't forget to subtract it, right? Because it's negative space. So it's pi radius squared times the height or the length, and in this case, it's negative pi times 0.5 squared, that's the internal radius, right? Times the length, 1.75 inches. That gives us a negative 1.3744468786 inches cubed. Now we do the math. We add the negative to the positive, and we end up with 1.718058482 inches cubed. Now that's our answer. That's the total volume of the cylinder now with the hole punched in it, the hole drilled in it or bored in it. Okay? Let's move on down. The second way is to find the total end area since it's uniform. Since it's uniform. This is a circular cylinder. It doesn't change in diameter. It's not a frustum or anything like that. All right? It's a right circular cylinder. So, excuse me. So, again, we have the outer radius of 0.75. We have an inner radius of 0.5, yes. Okay. Now, the diameter of the out is 1.5 inches. Is that not correct? 0.75 times 2 is 1.5. 0.75, that's the radius from here to here, times 2 is 1.5 inches. The inner radius is 0.5, or the inner diameter is 0.1, yes? All right. So the delta of the diameters is 0.5 divided by 2, which is 0.25. That's the wall thickness. So if you're trying to figure that out, trying to figure out what your wall thicknesses are, That's one way of doing it. Okay? So, there's no charge for that little extra tidbit there. Okay? So, when you get the blueprint reading, you'll be doing a lot of these. All right? You want to know what your wall thickness is? You take the outer diameter, subtract the inner diameter, divide that by 2, and that gives you your wall thickness. Now, let's go back to our volume. Okay. So our volume is the area of the base times the height. Now the height is the same for the negative and the positive space, yes? All right. The pi is the same. Pi is the same. So we're going to do radius. So you can take the radius of the out squared minus the radius squared of the inner, and then multiply that times pi, and then multiply that times 1.75, and you will get the volume of 1.718058482 inches cubed. Now, is this not the same number that we got up here? Well, let's go double check it. 1.71805, 1.718058482, yes? Well, looky there. All right. If you don't want to use radius and you want to use diameter for whatever reason, I don't care. Makes no difference to me. Then the volume is the area of the base with diameter. So how do you find the area of the circle? It's pi d squared over 4, right? Okay. So you're going to factor out pi and 4. So that's pi over 4 times the outer diameter squared minus the inner diameter squared. You get that number. So that's 1.5 squared minus 1 squared. That's 1. All right. Times 1.75 times pi, divide by 4, and guess what you get? Well, big surprise, right? It's the same as before. Is this not the same number as that number? Well, it is, and it's the same number as we did when we did the solid mass and subtracted the negative space. All right. Now again, what's the unit weight if it's made of steel at 489 pounds a cubic foot? Now, you already know the secret to this. We want this in cubic inches. Our volume's in cubic inches, so we take 489 pounds and we divide it by the equivalent of cubic inches that make up a cubic foot, which is 1728. And lo and behold, we still get 0.283 if we round it to 3 decimal places. Now, you may want to round it to 4. I don't know, and I don't care. It's up to you. We just go to 3 decimal places for this, for this course. All right, therefore, the weight is the volume, this right here, 1.71850 blah, 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 inches cubed, times the unit weight, which is 0.283 pounds per inch cubed. All right, the inches cancel out, the inch cubes cancel out, and we end up with a weight of 0.4862015 pounds. Okay. Now, what if this was made out of Inconel at $50 a pound? What if it was what if it cost $50 per pound? $50 per pound. How much does it cost? How much did it cost before we punched a hole in it? Well, this is after we drilled a hole in it, right? So we'd have to come up and get the larger number up here, right? To start off with. So we come back up here and we get the first volume without the hole, and it's 3.0925052. And I'm going to put that in my calculator because I'll forget it when I scroll back down. 0.92505.268, and that teaches me to hold so many decimal places. This right here is the volume as if there is no hole in it. Yes, that's the volume as if there's no hole in it. That's the volume as if there's no hole in it. So that's the piece that we started with. Yes? So now let's come down here. Let's find out what that piece originally cost us if it's made out of Inconel, which is at $50 a pound. So we're going to take the unit cost at per pound, and we're going to multiply it times what? We're going to multiply it times 3.09252505. Oh my God, 268. Ought to be whipped carrying all these decimals. That's over 1 because that's a whole number, 3.1. So we're just going to multiply that number times $50 per pound. The pounds are going to go away. Okay, this was pounds, right? So we're multiplying a fraction. We multiply the tops, multiply the bottoms. The pounds will cancel out, leaving us with what? $154.63. So that piece cost us $154.63. It's like 62.52634, but we're going to round it to 2 decimal places because it's money, right? So, all right. So that's what it would cost us. That piece of Inconel cost us that much money. Okay, so there's all kinds of things you can do with this. But anyway, this is our final weight with this 1.75 inch cylinder with the hole drilled in it. Now we can play this video back, the section of the video back, until you can get your head wrapped around how we did that. There's 2 ways to do it. If you don't like, if you're confused with doing these radiuses and the diameters like this, the in or out, then make it simple on yourself. Go back up here, calculate the positive space as if there's no hole in it, then calculate what the negative space is with this hole, the cylinder of air. Here, the cylinder of air. This in here, cylinder of air is negative. Subtract that number from the overall number like we did here, and you'll still come up with the same answer. Yeah? You'll still come up with the same answer. All right. So let's move on. What about the surface area of the solid? Well, what is the surface area of that solid? Well, let's go over here to our sketch pad. Let's see here. Because I don't think I drew a very good picture. Total surface area. No, we did. We'll use this. If we have to go over the sketch pad, we will. All right. The surface area of that solid is the circumference times the height or the length, right? Now, that's the side of the cylinder. We got 2 surface areas on the 2 ends, right? And that's the area of the circle. All right. So let's look at this. The outside diameter was 1.5 inches, yes? Times pi. Pi times the diameter is the circumference. So, times the length of 1.75. Now, you're not figuring out, this is the circumference, which is just in inches. This is the circle, the end circle. 1.75, right? 1.5, I mean. 1.5 diameter times pi, and that gives you the distance around the end piece. It gives you the distance around the end piece. But there's a lot of these end pieces stacked on top of one another, right? There's actually 1.75 inches of those end pieces. Okay. So let's take this. So this is the surface area of the side of the cylinder. Now we're going to do the ends, and there's two ends, are there not? So you're going to take pi times 1.5 squared. What's the diameter of the end piece? Yes, that's the diameter. What's the area of a circle? Pi d squared over 4, and there's two of those, times 2. Yes? So you do this math, and you come up with this number. Okay? That's the surface area of the solid. That's the surface area of the solid. Okay? Now what about the total surface area? Because we punched a hole in it, yes? Okay? Well, that changes. This up here is the surface area, the total surface area of the bar. This up here is the total surface area of the bar without the hole in it. Okay? This down here is this is how we're going to calculate the total surface area of the finished piece. So we have the ends. Now the ends have an outer radius or an outer diameter, and they have an inner diameter. That's the hole, yes? Okay. So what we can do is just calculate this surface area here times 2. So we have an outer radius, which is 0.75 squared, minus 0.5, which is that half inch, right, squared, times pi, times 2. All right. Now, that's the surface area of the ends. This is the surface area of the ends. Surface area of the two ends. All right. Now we want the surface area inside this tube. Now we did that on the scratch pad, right? So, what is the diameter? What's the diameter across the inside hole? Isn't that 1 inch? Of course it's 1 inch. So the circumference is pi d times, that's the circumference, that's the distance around the inside of the hole. But there's a bunch of those stacked on top of one another. There's 1.75 inches of those stacked on top of one another. So you take that circumference times the length. Here we go. Right? Times the length. The length is 1.75. And so the surface area on the inside of that hole is this right here. That's the surface area of the inside of the hole. Surface area of the inside. Now we want the surface area of the outside. Now we've already done that. We did that up here, did we not? It's pi times the diameter of 1.5 times the length. Yes? This is the circumference. This is the circumference in inches times the length. Another dimension, so that's inches times inches is inches squared, so that gives us surface area. So that's pi times 1.5 times 1.75, and that gives us 8.24668.076. Now, does that number look familiar? There it is right there. See, this is the surface area of the side of the cylinder, yes? And then that would be the surface area of the ends without the hole in it. Okay, so without the hole, the total surface area is 11.78. And so this number here is the same as we got before because it's just dealing with the surface area on this outside up here. Right, all the way around it, all the way down. Remember that here are the ends, and there's the inside of the hole, and then here's the outside. We add up all that surface area, and we end up with a total surface area of 15.707 compared to 11.78. Compared to 11.78. So we've increased the surface area, but we've decreased the volume. Now that's how heat exchangers work. That's how your radiator works. It's got more surface area so the air can transport through it. So we've increased our surface area if we had to coat this thing or paint it. But we've decreased the volume. Thus, we've also decreased the weight. So we reduced the volume by drilling a hole through the center, but we increased the total surface area. This is how heat exchangers and cooling coils work, by increasing the surface area. Now we've already talked about negative space and positive space. So don't forget the mysterious case of the donut hole. Okay? So the next time you go to a donut shop and your kids want a bag of donut holes, just get them an empty bag and start the math lesson with them. They need to learn early on that not everything that's advertised is true. So, and they probably won't have issues when they understand they're eating balls, donut balls, that is. So, they'll get over it. All right. Let's see. Okay, on the threading, which we already had a video on the threading up in the threading lesson if you watched it. It's required reading on D2L, the formula sheet, and the document. So the number of threads, we're going to reiterate this. We're almost, we're running on 32 minutes, so this won't be too bad. All right, the number of threads, either in a threaded hole or threaded part, or the number of threads along a line, is the thread depth or length times the TPI. So if you have 1 inch and the TPI is 24 TPI, 24 threads per inch, and it's 1 inch, guess how many threads you got? 24. Wow, isn't that cool? All right. Or if you're dealing with pitch only, and remember, if you remember that video, in metric land, for a metric thread, there is no TPI because there's no inches. So a metric thread would be like an M10, that's the nominal diameter, let's say 1.05 or something like that. That's the pitch. Whereas an American thread or an ISO thread would be like a 3/8 by, I don't know, how about 14 TPI. So this is the TPI. So it's 14 TPI. That's not the pitch. The pitch is 1/14. Okay? But that's not how you buy ISO threads. You buy it 3/8 by the TPI. Metric, you buy it the nominal diameter, which would be 10 millimeter in this case, just like this is supposed to be 3/8. If you measure it, it's not quite 3/8. You measure this, it's not quite 10 millimeter. And this is the pitch. Okay, all right, enough of that. So, the number of threads is the thread depth or length times the TPI, or the thread depth divided by the pitch. All right, thread depth divided by the pitch. Now, the pitch is equal to 1/the TPI. Now, this is a repeat. All right, pitch is 1/the TPI. So if you're going to divide by the pitch, you take the depth divided by 1/TPI. So that's going to be the thread depth over 1, yes, because it's a whole number by itself. So that's a fraction divided by a fraction. And how do you divide a fraction by a fraction? Well, we turn this thing upside down and multiply it to the top, right? So that means it's the thread depth over 1 times the TPI over 1. So now you're back at the thread depth times the TPI. Okay. So we talked about the lead. The lead is the distance a threaded fastener travels in one 360-degree rotation. In one 360-degree rotation, starting at 0 and rotating around to 360, one full revolution. a one start thread, the lead is equal to 1 times the pitch, or 1 times 1 over the TPI. A two start thread, the lead is 2 times the pitch, or 2 times 1 over the TPI, since 1 over the TPI is the pitch. A three start thread is a three start thread. The lead equals 3 times the pitch, or 3 times 1 over the TPI. Now here's an example. This will be what's on the exam. Here's an example. There'll be a bunch of these. And one of the questions says, if hole B is now a two start thread and it rotates 2 times, most people just do the 2 times the pitch and give me that, but it's really not. It's 2 times 2, right? Because we rotated it twice, not once. So don't fall for that. Okay. Now, so let's say the hole is 3/4 of an inch and it's full threaded. We want a full threaded 3/4 inch hole. Okay. All right. Or actually, we would do something like that for drawing it. Whatever. And the pitch is 1 over 24. And we said the pitch of the threads is 1 over 24. Now, if the pitch equals 1 over the TPI, and the pitch is 1 over 24, what's the TPI? It's 24, right? Okay. So when I ask you what the TPI of the hole that has a pitch of 1 over 24, you're not going to be a goober and not put 24 here. 24 goes there. That's the TPI, right? As I said, the pitch is in fractional form. The pitch equals 1 over 24. The definition of pitch is 1 over the TPI. So who's buried in Grant's tomb? It's not Grant's wife, it's Grant. All right? So, so in this case, the pitch is 1 over 24. It's 3/4 of an inch deep. The TPI is 24. And so we're going to multiply 3/4 by 24 over 1, right? Because what's the thread, how many full threads are in a hole? It's the thread depth divided by the pitch, or 1 over the TPI. And how do you divide a fraction by a fraction? You turn this upside down, right? You turn it upside down. In other words, it was 3/4 divided by 1 over 24. Yeah. So how do we do that? We turn this upside down. We multiply this by 24 over 1. 3 times 24 is what? What is that? 3 times 24. Well, 3 times 4 is 12. That's 72, is it not? 72 divided by 4 is what? Isn't it 18? I think I screwed that up. No, I didn't. Yeah, I did. 24 times 3 is 72 divided by 4 is 18. No, I didn't screw it up. I don't know what's wrong. Maybe it's time for a bourbon. It's past 6 o'clock. So it's 18 TPI. Now, if this if this answer came out to a decimal, let's just pretend. Let's pretend we're in Never Never Land, okay? And Tinkerbell's messing with us. And this answer came out to 18.9. We don't round up. We forget the decimal when we're talking about the number of threads, because a partial thread does us no good. We only are interested in the whole number. So I don't care what it is. If it's 7.56, if you give me that answer, it's wrong. It's only 7 threads. It's not 7.5. It's not 18.9. It's 18, or it's 7, or it's 6, or it's 5. It's just a whole number. So I think this pretty much covers everything. You know, we're running at about 39 minutes for this. I think I've covered it. This was covered in a previous video. It's being recovered now. So don't fall for this. The distance traveled in one revolution for this hole. in one revolution, if it's a one-start thread, and it's a one-start unless you're told otherwise, how far is it? A one-start. The lead equals 1 times the pitch, or 1 times 1 over TPI. So it's going to travel 1/24 of an inch in one revolution, or the real answer is 0.0416666666, the number my ex-wife thinks tattooed on the back of my head. Okay? That's how far it travels in one revolution. One revolution. One revolution. Now, we have a few minutes left, I think. And I think that's it. Now, if we said hole A was a 2-start, let's pretend hole A is a 2-start thread. Pretend. Tinkerbell. 2-start. And we want to know how far it travels in 2 revolutions. Well, in one revolution, it's going to be 2 times 1 over the TPI, right? 2 times the pitch, 1 over the TPI. But this thing traveled twice. We said in 2 revolutions. So we're going to multiply that again by 2, yeah? So that's 2 over 24. Which is 1/12 times 2, which is 1/6, right? So, if it's 1 over 24, then it's 2 times 2, or 4 times 1 over the TPI. 4 divided by 24 is 0.1666666, okay? Right? You get that? Everybody get that? Draw down here, I can draw down here, right? So that's 2 times 1 over 24 equals 2 over 24. That's for one revolution, yeah? But we did this twice. We rotated this thing twice, so we're going to multiply it by another 2. So now it's 4 over 24. Or it's 1/6 of an inch. And because we're machinists, you're going to give me the decimal equivalent, right? So 6, excuse me, is 0.0.166666. Ooh, there's my favorite number of mine that my ex-wife thinks tattooed on the back of my head. Ooh, the Antichrist. All right. So, now, just for grins, we're at 43 minutes on this video. Let's go over here to the pad and let's select and get all this out of here. Let's select and get all this out of here. Now, in machine land, we have what's called a micrometer, right? Okay. We have a micrometer. Now, the micrometer has an anvil, just like that thread micrometer I showed you. It has a spindle. Here's the anvil. The spindle comes through here, through a hole. It has a thimble and a ratchet. And in one revolution, one complete turn of that micrometer, this thing moves. This thing moves in one revolution 0.025 inches. So in one revolution, that's how much it moves. That equals the lead, does it not? So the lead equals 0.025. Now, what did we say the lead was for a single start thread? We said the lead was 1 times the pitch, yes? 1 times the pitch. Lead equals 1 times the pitch. And we also said that the pitch was 1 over the TPI. So let's find out what the threads per inch are for this screw inside this mighty fine micrometer. So we'll fill in what we know. In this case, we said the lead was what? 0.025 inches, yes? And we said that's going to be equal to 1 times 1 over the TPI. Right? So we want to figure out what the TPI is, do we not? Okay. We can do this one of two ways. We could have said up here as 0.025 equals 1 times the pitch. Spell it right. Pitch. And we can do that. So let's do that. So we want pitch by itself. So we're going to have to divide both sides by 1. So let's go here. 1.025 equals 1 times the pitch. So we divide this side by 1. That's how we undo multiplication, right? And what we do on this side of the equal sign, we have to do over here, yes? We divide that side by 1. The 1's go away. The 1's go away. And so, what do we get? We get pitch is equal to 0.025 inches. Well, that didn't tell us anything. I want to know what the TPI is. Okay, pitch. All right. But we also said that the pitch is 1 over TPI, right? Now I'm going the long way around the barn on this. TPI, right? So what we're saying is that 0.025 is equal to 1 over the TPI. So now what the hell are we going to do? Well, that's over 1. We want to know what the TPI is, right? Well, remember that thing about cross multiplying? Looky here. We can cross multiply, can't we? Cross multiply. So we get 1. If we do that, that's 1 times 1 is 1. Y'all are probably thinking I really need that bourbon right now, don't you? This is 0.025 times the TPI. The point of me doing it this way is so I don't want you to get all freaked out, okay? There's always many ways to do stuff. So, and we want to know what the TPI is. So we've got 0.025 times the TPI. Well, how do you undo multiplication? You do it by division, right? So aren't we doing the same bloody thing? We are. 0.25. It's just numbers, dude. Or dudettes, or math people. Y'all probably really think I need my bourbon now, don't you? Well, it's almost time. So we're going to divide this side by 0.25 because there are no isms in math. No isms in math. That's why I like it, math. Okay? The equal sign, algebra from the Arabic to fix the halves. The redneck Europeans didn't have the bloody equal sign until the Crusades. All right, so what happens here? This cancels out, right? This leaves us TPI equals 1 over our lead, right? 1 over the 0.25. Oh my God. 1 over our 0.25. Okay? So take your modifying calculators out and divide 1 by 0.025. And what do you get? You should get the TPI of 40. You should get a threads per inch. Threads per inch equals 40. 40 TPI. TPI. So, if you have a fastener that's 40 TPI, then you know that in one revolution, it will move 25 thousandths of an inch. This is 25 thousandths. That's one revolution of a micrometer. 25 thousandths. That's the tenths, hundredths, and thousandths place. 25 thousandths of an inch. So you can make your own jacking screw if you want to move a motor plate around or something like that. Just cut you a 40 TPI thread. Or if you can't cut a 40 TPI thread, you can get a 24 TPI bolt and nut at the hardware store. You can figure out from these equations in one revolution how far that thread will put, that threaded fastener will push that motor base over in thousandths of an inch with one revolution. You know, you loosen these bolts up and kick that puppy around, put your dial indicators over here, and it'll help you align that so you can make your own little jig. All right, so that ends this video, and boy, we burned up 51 minutes, but thank you for your patience, and that ends part 2 and the last part of the review for exam 2. All right, so good luck.